Oh, yes. Good hope. Yeah. Hello, hello. Yeah. This link. That meeting link. Okay, launch the meeting. Meeting link is in the mails. Please. Zoom. No, I think that number I have. Is this on?
With everything you can, everything is okay.
Yeah. Okay. Is it this link is working? Different date actually. Okay. Fine, no? We have to take out. So YouTube we have to go for. Yeah. Yes. Thank you, Ranjan. Sorry, right? Okay. So first of all, I would like to thank the organizers, Dr. Sunil and Dr. Arijit, for the invitation, and definitely Professor Deshmukh. It has been wonderful, actually, means knowing you for such a long time, and I always cherish our time that we spend together. Okay, and thank you for the invitation. So today I am going to present something on valley polarization in two-dimensional borocarbonitride system. So can you just switch off this light here, because maybe this is very faint. Yeah, thank you. Yeah, so borocarbonitride system, this is something that we have started working in our group in less than 2 years actually. Okay, and we have got some really fascinating and encouraging results lately. I will tell you what do I mean by valley polarization, why do I need to go in 2 dimension, and what is the necessity of this borocarbonitride system. So the total theme of the talk is actually, at the outline of the talk, is actually condensed in the title itself. Okay. So we know that there are semiconducting materials which are characterized by a gap delta between the band edges, which is actually the valence band maxima and the conduction band minima. Okay, anyway, this is not working, but I think that okay, that's fine. Just the laser is not working, changer is working. Yeah. So the valence band maxima and the conduction band minima, and the gap is actually delta. So with this particular gap, we can characterize the semiconducting material. But there are certain class of semiconducting material where actually there are 2 different locations of the band structure or in the momentum space at minus and the plus momentum. Okay, same momentum. In these 2 cases, actually, these 2 particular momentums, the band edges, they are actually degenerate. That means both the band edge positions for the conduction band maxima and the valence band minima, they are exactly same. So they represent exactly the same gap. Such kind of material we call as a time reversal symmetry is there actually, and time reversal pair these 2 locations. Okay, now these 2 locations we call actually the valleys. Okay, so minus k and the plus k, these 2 momentums, they actually represent 2 valleys here, because these 2 are the minimum energy gap in this particular material. So the question is that although these 2 band locations at these 2 momentum, they are actually having the same band gap, they are actually coming from 2 different momentum as a time reversal pair, plus minus k. My question is that if I shine light on this particular system, and let us assume that the optical selection rule actually allows the electron to be transferred from the valence band maxima to the conduction band minima. Optical selection rule actually allows us that. So in that particular case, if I actually can give exactly same wavelength of light, and if I shine that light, I would expect that electrons will be actually transferred from the valence band maxima to the conduction band minima, and this should actually happen in both the valleys in the same band structure. Okay, if it happens actually in both the valleys, that's not really very interesting for me. What I want actually, I want to discriminate between these 2 valleys, and I want selective electron excitation only in a single valley, although they are representing the same gap. So either it will be happening at minus k or it will be happening at plus k. So first what I will do actually, I'll go through the simple mathematics of how I can actually create that asymmetry between these 2 valleys, so that it will actually take care of optical excitation only in a single valley, and then I will actually tell you what are the implications of that, how that will be useful to us. Okay, yeah. Yes. But it might not happen that they will happen in some particular valleys only. It's not possible, maybe all the time. I'll come to that particular point also. So the band edges that I am actually seeing, it will be much more easier for me or much more efficient for that particular material if that happens at a high symmetric point. I'll come to that point also. So I need this band edges happening at the high symmetric point. Okay, high symmetric point. So now what I'm going to do actually, before I go further, I will designate these two bands or these two momentum with two different indices, tau equal to -1, tau equal to +1. And this particular tau I will come later actually, how that will enter into the Hamiltonian, I'll come later. So what I'm doing here, I have the two values, and these two values I have actually indexed with tau equal to ±1. Okay. Now, as Ranjan was asked actually, so I have one very ideal material in that particular sense, which I call graphene, which is a hexagonal carbon two-dimensional plane. Okay, single atom thickness, and this is the lattice of graphene. Pardon me that my laser pointer is not working, so I'll be using my hand for that. So this is a honeycomb lattice, you can say, just like the bees actually, that honeycomb lattice it is actually. And this black and white, they are the two different sublattice points, and they are actually contained within this rhombus unit cell. This I named as A and B sublattice points. And since this is a rhombus unit cell, from the very basic solid state physics, we know that this will actually give rise to a hexagonal first Brillouin zone for me. Okay, now this hexagonal first Brillouin zone, if I am to look into, so the center of the first Brillouin zone is the gamma point. And if you see the corners, there are two non-equivalent corners that I have actually named here. One is K and another is K prime. Now, if I consider this as the gamma and this as the X axis, actually, immediately you can see this K and K prime, they are equidistant from this gamma, which is the 0, 0 of the first Brillouin zone coordinate system. Okay, what does that mean? If that is happening at +K, this must be happening at -K. So I can consider these two as the two values. Now, if I see the band structure, here I have plotted the valence band and the conduction band. Since it's a two-atom unit cell, so simple tight binding calculation will give me only two bands here. Okay, single orbital picture. So this valence band, the conduction band. And now if you see the dispersion, there's something very unique dispersion is actually happening here. This is the hexagonal Brillouin zone, this black line, and that is happening at 0 as a Fermi energy. At Fermi energy, the valence band and the conduction band, they just touch at a single point. They just touch. There is no overlap. And this touching point, if I just emphasize on that particular region, I would see that this actually represents a conical dispersion. Okay. So this conical dispersion, that means if I take the cross section of this conical vertically, I'll get two straight lines intersecting each other. Okay. What does that mean? We know that energy goes as p square by twice m. So energy is actually parabolic with momentum. Okay. But when I have this dispersion relation, energy goes linear with p. And this actually represents a unique scenario, which is called the Dirac electrons here. Okay. And I call this particular cone as a Dirac cone, and this point as a Dirac point, where the top of the valence band, top of the valence band, the conduction band, they actually touch each other. Now, this actually represents a massless Dirac fermions in this graphene. So the valence and conduction band, they touch conically exactly this K and K prime points. So now immediately we can see at Fermi energy, there is no gap between the K and K prime at the K and K prime values, in these two values. And if there is no gap, actually, this is not a semiconducting system. So whatever I had actually shown that I need two values, I need some energy gap and all these things, immediately I see that that is not satisfied with this particular material graphene because I do not have a gap here. So there is no question of any excitation or anything. So whatever I need for electronic excitation, graphene is not the material that I should be actually looking for. So I need some further modifications in that particular thing. But no matter, this K and K prime, I indeed see two valleys. Although there is no gap, there are two valleys, and these valleys, they will valley pseudo spins. Why I'm calling pseudo spins actually, you know that in spin structure, if you see, you consider the up spin and the down spins. These are the two spin degrees of freedom that actually consider. Okay, but instead of two spins, we can actually consider this K and K prime valleys as a two different degrees of freedom, just like the spins. So that is why the valleys itself I am calling as a pseudo spins, as if the valleys are actually working as a spins, although I do not have any gap here. But indeed, this K and K prime, they are actually time reversal pairs of each other. Okay, this is the graphene. Now, I'll again come back to this particular graphene, but now we understood that graphene is not a good material for the valley polarization because I do not have any gap here. Yeah, sure. These are also time reversal pairs actually. It depends on me actually how you consider the axis, right? Yeah. So they are all time reversal pairs. All these K prime, they are time reversal pairs. Okay. Now, let me actually take little digression actually, and I'll again come back to whatever we have discussed. I'll show you the semi-classical equation of motion for the block electrons under the applied electric and the magnetic field. So the applied electric magnetic field is actually written in that particular form here. And this is the equation of motion. That's R dot represents the velocity of the block electrons here. Okay. Now you see here the second term, I have the K dot cross something called omega. And cross product means this omega, when I actually take, the sign of the omega actually matters. Because if I change the sign of omega, the direction of R dot is going to be changed because it's a cross product that I am actually taking here. Okay. Now what is omega? Omega is something called the Berry curvature. This is a second rank tensor actually in terms of the Berry connection. Okay. This A is the Berry connection, which is actually analogous to the vector potential. So from this particular equation, I can say that Berry curvature, this equation, if you see of the Berry curvature, this equation actually looks like a magnetic field in the electromagnetic theory. Okay, so I can actually say that Berry curvature that can actually act as a pseudo magnetic field, which is analogous to the magnetic field in the electromagnetic theory. Okay, so this is a Berry curvature and the expression for the Berry connection that I have actually written here. Okay, now the Berry curvature can be calculated in terms of this particular equation. Okay, where this P is actually represented by this one, UN, V, Ui. These UNs are the periodic block wave functions and the V is the velocity operator. And there are two different such terms comes in the numerator and the denominator. I have the difference between the energies of these two particular states. Okay, now this particular expression actually tells me that this Berry curvature, this is under time reversal symmetry. It's actually an odd function. I go from K to minus K, Berry curvature changes its sign. But it is actually even under the inversion symmetry or the special inversion symmetry. That means if I change K to minus K, the sign of the omega does not change. So it is odd under the time reversal symmetry and the even under the inversion symmetry. All of us actually know immediately that these two conditions cannot be satisfied simultaneously. Right? These two conditions can never be simultaneously satisfied. Because if I go to K to K to minus K, time reversal symmetry demands that this should change its sign. But this demands that it should not change its sign. So both of them cannot be satisfied simultaneously. So I can say that under what condition both of them will be satisfied? When the omega is actually equal to 0. So when I have both the symmetries in the system, my Berry curvature must be equals to 0. When my Berry curvature is 0 in a particular system, I do not have any pseudo-magnetic field acting in that particular system. Okay, I started with the discussion that I needed two valleys. Why? Because I need to excite the electrons. Okay, so I need two valleys and I want to discriminate between these two valleys. So I cannot touch this particular symmetry. I need the time reversal symmetry for my purpose. Okay, so the symmetry that I can actually play around, that is a inversion symmetry. And to have any non-zero omega actually, I need to break the special inversion symmetry. Yeah. Sorry? That you are changing here. No, not x actually. That you can derive from this particular function once you include this block periodic part actually. Exactly, then it becomes that. Once you include this one here, okay, then actually you can see that with the special inversion symmetry, you will have this one. This is special inversion in X. You are absolutely right. In X only, in real space only, not in momentum space. But once you include the block equation here, actually, you will get that condition. Okay. So what I am going to do actually, I am going to break the inversion symmetry, and that is the reason I have taken that borocarbonitride system that I had actually considered. And I will show you actually why do I need the borocarbonitride system to break the time special inversion symmetry. Now again, I came back to the graphene. I told you that graphene anyway, I do not have any band gap, so it's not good for the optical excitation. On top of that, in the graphene rhombus unit cell, I have the two carbon atoms. When I have two carbon atoms, I do not have any inversion symmetry also. Okay, sorry. Oh, I have inversion symmetry. This is wrong. So I should write that inversion symmetry or no broken inversion symmetry. Okay, this is wrong. Okay, so I have inversion symmetry here because if I put the inversion symmetry here, I'll get the carbon atoms here. I want to break the inversion symmetry. What I have to do actually, I have to change 2 atoms in the graphene unit cell, 2 different atoms if I can put. Okay, what I can do, I can take graphene, I can put 2 different sublattice potentials. Okay, if I put different sublattice potentials, there is imbalance between these 2 in the same unit cell, and I have broken inversion symmetry in that particular case. Okay, my question is that does it relate to any particular experimentally observed material? Answer is yes. We can actually correlate this particular system with the hexagonal boron nitride system, which actually represents the same honeycomb lattice, and in the unit cell you have the boron and nitrogen. Okay, same graphene like lattice, but you have in the unit cell boron and nitrogen. So I can say this is hexagonal boron nitride system. So according to whatever theory I have just explained, hexagonal boron nitride system should actually show me valleys, gapped valleys, and I should have 2 different Berry curvatures in these 2 valleys, right? Okay, I'll come back to this particular point again. Sorry, I'll show also. This is highly band gap. I'll come to this point little later. Okay, I'll show it. Another such material which actually breaks the special inversion symmetry, that is the monolayer of the transition metal dichalcogenide system here. Okay, this is trigonal biprismatic structure. Okay, trigonal bipyramidal structure. Okay, so I have at the center molybdenum or the tungsten, and at the top I have the 3 sulfur of the selenium or the tellurium atoms. They are actually sitting in this way. So as if the MO or W that is sandwiched between 2 layers of sulfur of the selenium. Okay, this also lacks the special inversion symmetry. Okay, and what it does actually show, if I calculate the Berry curvature omega, I see at K and K prime point I have opposite Berry curvatures. Okay, why is it so? I do not have any special inversion symmetry, but I do have the time reversal symmetry intact. So under these 2 conditions, I have opposite Berry curvature at the 2 valleys K and K prime. What does that mean? At 2 valleys K and K prime, I have the pseudomagnetic field, non-zero pseudomagnetic field acting in opposite directions. So when the electrons actually flow through this in the momentum space, if I consider, they experience upward direction magnetic field at K valley, downward direction magnetic field at the K prime valley. So 2 different directions. Now if I consider the Lorentz force that the electrons are actually facing, Lorentz force actually will be acting in the opposite direction because I have 2 different directions magnetic field working there. Okay, this is at the 2-dimensional dispersion. The same thing I have shown here, but in 2 dimension, where you have this hexagonal K and K prime, and you can see positive and the negative. I want you to notice, if you can see these values, this is actually going from +80 to -80 in the atomic units. Okay, why this value is important actually, I'll come shortly. Okay, now with all these things, if I consider now this K dot P Hamiltonian at the band edges in the vicinity of this K and K prime point. Okay, so this is the K dot P Hamiltonian, and if you look at the Hamiltonian, I have the terms A is the lattice constant, T is the hopping integral, delta that is a band gap, sigma is a Pauli matrices, and the tau that is appearing at the first time here, that's the valley index. Okay, with this K dot P Hamiltonian, now if I actually solve the Hamiltonian, get the wave function, put those wave functions and those velocity operator in between, then I can calculate the Berry curvature, whatever I showed just 2 slides back. Okay, once I calculate the Berry curvature actually for the conduction band appears to be this one, for the conduction band. Why I'm mentioning conduction band? Because if you actually calculate for the valence band, this minus sign will be plus sign. Okay, then what will happen? At the same K, valence and the conduction band will be having 2 opposite Berry curvatures. At the same K value, valence and the conduction bands will be having opposite Berry curvature. Now, this tau, I told you that tau can have 2 different values, +1 and the -1. We have started with that. Let us consider only the conduction band at K and the K prime. At K, tau is equal to -1. If tau is equal to -1, my Berry curvature is positive. At K prime, tau is +1. My Berry curvature is negative. Okay, so according to this Berry curvature equation, I can immediately say that at K and K prime, I have two different Berry curvature for the conduction bands. If I see the valence band, it is just the opposite way around. Okay, so at K value, my Berry curvature is positive at the valence band, negative at the conduction band, and it is just opposite when I go to the K prime value. Okay, now I will show you the optical selection rule in presence of the circularly polarized light. The sigma plus minus, sigma plus represents the right hand circular polarized light, sigma minus represents the left hand circular polarized light. All of us know that how to generate the circularly polarized lights. And this one is the coupling strength of the optical fields. Okay, and this is actually given by this particular equation. Okay, so here I have actually given. So what I want you to notice here, for the optical transition in the vicinity of the K and K prime values, in the vicinity of the K prime values, I have this particular relation. Okay, where this P plus minus, this plus minus actually is coming from the sigma plus minus. So this plus stands for the sigma plus, that is right hand circular polarized light, minus stands for the negative, that is a sigma minus, that is a left hand circular polarized light. I have this particular equation. Now, if you see in the denominator, I have delta square plus this one. This ATK, S square, T square, K square, this ATK, that actually represents the slope of the curve, slope of the band structure. So near K or K prime values, we know that the slope is almost next to 0. Okay, because I have a maximum or the minimum. So if the slope is actually close to 0, that must be extremely smaller than the delta that I am actually considering, because I have a gap system here. Okay, so in that particular case, I can actually ignore this term with respect to this delta square term. So I'll be having square root of delta square in the denominator. So delta here, then delta will come here, delta will cancel. I'll have 1 plus minus tau. Okay, now look at this one. 1 plus minus tau. Let us consider for the K value, I have tau is equal to -1. I shine right hand circular polarized light, that means plus sign will be surviving, no minus sign here. So I have 1 plus tau at K value, tau is equal to -1. -1, they will cancel, it will be 0. So the right hand circular polarized light, which is represented by plus, that doesn't couple with the K value. So it cannot excite any electron at the K value. I consider tau is equal to +1, that is at the K prime value, considering still that is a plus. Okay, so now this is 1 plus 1, 2, this is non-zero. So what does that mean? If I put the sigma plus light, that is right hand circular polarized light, that will selectively excite electrons only at the K prime value and not at the K value, although their gaps are actually exactly same. Okay, what will happen when I take the minus sign? It will be just the opposite one. Then what will happen? The left hand circular polarized light, it will excite the electrons only at the K value and not at the K prime value. So what I have to do, I have to shine the lights with the two different circular polarization, and thereby I can actually regulate that which value actually the electron will be getting excited, either at the K value or at the K prime value. Now what is the implication of that? So exactly, but there are something more about that. I'll come to that point also. Okay, so whatever I have just discussed, I have pictorially actually put it here. At the K value, I have tau equal to -1, K prime value tau equals to +1, and Berry curvature, actually I have seen that +1 and -1 at the K value, -1 and +1 at the K prime value. So I know that the electrons will be excited by the right hand circular polarized light only at the K value and left hand circular polarized light only at the K prime value. Okay, that's what the optical selection rules are actually telling me. Okay, now what is the implication? I'll come to your question that what is more about this one. So I already have shown this equation of motion, right? Now look at the equation of motion. If I consider the electron conduction will happen through the valence band, sorry, the conduction bands. Whole conduction will happen through the valence bands. At same value, the valence and the conduction band are having opposite Berry curvatures. At the same value, opposite Berry curvatures. If it is having opposite Berry curvatures, so the electrons and the holes will be having opposite sign of the Berry curvature, they will be actually facing. Okay. So now consider the drift velocity. You shine sigma plus light. You apply the external electric field, in plane electric field. Magnetic field is already there in terms of the pseudo magnetic field because the Berry curvature is already there. So the electron drift velocities now you consider actually electrons and holes, they will actually move in the opposite direction. Because the conduction band and the valence band, they are having opposite Berry curvatures. So the electrons and holes, they are actually facing two different pseudo magnetic fields, different direction of the pseudo magnetic field. So the electrons will come this direction when I apply the in plane electric field. Holes will be drifting towards the opposite direction. What will happen if I, instead of sigma plus, think about this one, when I shine the sigma plus, there is no excitation in the other valley at all. Now I change the circular polarization of the light itself. Okay, now what will happen? The previous valley, there is no electron excitation, only the other valley, now the electron excitation will happen. And in that particular case, since now the conduction and the valence band, the sign has changed. Okay, this electron and hole, now they will start going in the opposite direction. Now in the electrons will go to the upper edge, holes will be moving to the lower edge. Okay, so what exactly you are doing? You are not changing the applied electric field. Magnetic field has been taken care by the pseudo-magnetic field or the Berry curvature of the material itself. I am just shining the sigma plus or the sigma minus. Just by shining to different circular polarization, I can control which direction the electrons will flow and which direction the holes will actually flow. Okay, so this is actually the Hall conduction arrangement. Okay, so basically we can actually end up with the valley Hall current here, and that valley Hall current direction in terms of the electron and the hole, you can actually control just by shining to different polarization of the circular polarized light, right-handed or the left-handed circular polarized light. So what exactly it is actually giving you? It is giving you the full control over the electron conduction and the hole conduction. So the two valleys you are actually using as 2 degrees of freedom with full control in terms of the sigma plus and the sigma minus light. So in this particular case, you really do not need to have the up or the down spins to have the spin currents. Rather, instead of the spins, you are using the valleys. So that is why I call this the valley pseudo spins. So you're using the valleys and you are having the valley current, and as per your wish, actually, you can change the valley current. That is actually called something called valleytronics. So now one can actually fabricate the device by exploiting the valleys of a particular material, not the spins or anything. Okay, so exploiting valley degrees of freedom actually can give you the different kind of electronic device applications, and that is called the realm of valleytronics. Okay, now something more interesting can actually happen when I bring the spin orbit coupling in the system. I have shown you one transition metal dichalcogenide system. Okay, so in that system, the spin orbit coupling is non-zero. When you do not have, when you have the spin orbit coupling, you have the last term, extra term is actually coming there. Lambda is the spin splitting because of the spin orbit coupling. Just think about this one. If the spin orbit coupling is not there, lambda must be equal to 0. It will actually end up with the normal k dot p Hamiltonian. When you have the spin orbit coupling, you have the third term also surviving. Lambda is actually non-zero. Okay, so in that case, what will actually happen? The Berry curvature will actually look like this, and I'll be having, instead of delta, I'll be having delta prime here. Delta prime is delta minus this term. So the spin splitting is also coming in this particular case. What exactly the spin splitting is doing in this case of transition metal dichalcogenide? They are splitting the valence band, but they are not splitting the conduction band. In dichalcogenide system, they are not splitting the conduction band. That's precisely what I have shown here, that this red is representing the upspin, blue is representing the downspin. So at the beginning, you had both an up and down spin. They are actually degenerate to each other. You apply the spin orbit coupling in terms of considering the transition metal dichalcogenide, your valence band gets splitted. When your valence band gets splitted, one of the valence band is represented downspin, other valence band represented the upspin. You go from k valley to the k prime valley, the spin index that actually switches. This is down up, this is up down. So here the topmost valence band is actually upspin. Here the topmost valence band is actually downspin. So now at k and k prime, the topmost valence band is upspin, and another value is topmost valence band is downspin. Now think about whatever physics just now we had actually discussed, that if I shine sigma plus or the sigma minus, I can selectively excite electrons either at k prime value or at the k prime value. Now in addition to that, I am further commenting that it is not just excitation at the sigma at the k value or the k prime value. I am exciting only the down spins at k value, because this is the topmost valence band. And spin of the system also when I have the non-zero spin orbit coupling. Sorry? No, absolutely not, because only the sigma plus will excite here. I shine sigma plus, only the up spins will get excited. I shine sigma minus, only the down spin will be excited. Isn't it? Because the Berry curvatures are different in these two cases. That we already have seen. But in addition to that, once I have the spin orbit coupling in the system, I have this kind of spin splitting also. The moment I have the spin splitting, here I can have this one. So now question is that if I apply the sigma plus, can I excite the down spin? The answer is no. Because in presence of the sigma plus, only this value the excitation will happen, and the topmost band representing the upspin only. So now in addition to saying that excitations are happening at k value or the k prime value, I will also additionally say that at k value only the upspins are excited, at k prime value only the downspins are getting excited. This is something called the spin valley locking. As if the valley and the spin, they get locked actually. Okay, now there has been many studies that whether I can break this spin valley locking. Now whatever you are saying, I apply the sigma plus and I want to excite either the upspin or the downspin in either of the valleys. I apply sigma minus and I can actually excite either of the plus or the minus valleys in presence of the spin orbit coupling. What will be the advantage of doing that? I already have the valley degrees of freedom here. In addition to that, if I can exploit the spin degrees of freedom also, up and down, right? I have k prime, up and down. Multiplication of 2 and 2 will give me 4 degrees of freedom. Now think about that. Plus and the minus, okay, of the spins, up spin or down spin, they can be used as the zeros and ones for the magnetic data reading. Okay. So what are the binary numbers we actually consider for this upspin? We can take the combinations of 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 combinations we can actually take for the spin multiplicity. Instead of these 2 bits per site, if I have 4 degrees of freedom, think about that, how many pairs that you can actually generate. 4 degrees of freedom. You have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Like that, so many configurations that you can actually make. That will be having huge advantages actually for the quantum computing applications also. Okay, or the information. If I can have the spin and valleys, both degrees of freedom available to me. Okay, so there has been many works are actually going on that particular aspect. Yeah, please. No, it is not obvious. This is special to this particular material. There are examples where the valence band, they don't split. Conduction band gets split. There are examples where even in presence of the spin orbit coupling, actually, both of them get splitted. But the splitting may be unequal. Okay, for the upspin and downspin. For this particular system. Now people are actually looking for whatever you are saying, that's the motivation that we are having, to have both the valley and the spin degrees of freedom available. Okay, so it will be advantageous if we have the splitting here also. Okay, one can selectively control both the up and the down spins here. Okay, now let me again come back to graphene. Yes. So, okay, this actually depends on the construction of the Hamiltonian here. Okay, this is special to this particular symmetry, that much I can actually tell you at this moment. If you derive that, it will be very clear to you. Okay, so whatever I showed, this 2H structure of this particular system, you construct a simple tight binding model, you will end up with this particular splitting once you include that lambda term here. Okay, fine. Now, I again go back to the graphene that I have discussed, and I told you that there are 2 drawbacks here. First, I do not have any gap here. I do not have broken inversion symmetry here. There is no way that I can get polarization here. right? At the two different values. So it's called a valley polarization. I will not have the valley polarization. But graphene has some interesting property like this bipartite lattice. What is the meaning of that? In bipartite lattice, if one of the sublattice prefers the upspin, other sublattice will prefer the downspin. So A and B sublattice will be preferring up and the downspins. So in a 2D plane, you have same number of A and the same number of B sublattice points. All the spins cancel each other. You do not have any magnetism here. How do you have magnetism? If you can create imbalance between the A and B sublattice point by creating some vacancies. Okay, is there any other way? So that any other way actually leads to something very interesting. This two-dimensional graphene, if I cut along a particular crystallographic direction, I can actually make this kind of ribbon structure. Now, if you look into this ribbon structure, I have zigzag edge in both the sides. When I have the zigzag edge in both the sides, now if I actually solve the Schrodinger equation with this zigzag boundary condition, all of us actually solve this particle in one-dimensional box problem and all these things, right? So I'll solve this one with the zigzag boundary condition here. And within the tight binding model, which is a non-interacting model, I'll actually end up with this particular band structure if I solve the Bloch's equation. Okay, what I will get? The top of the valence band and the bottom of the conduction band at u by t equals to 0 means I do not have any correlation here, only the simple tight binding model I'm using, and partially flat band I am actually getting. This is the Dirac point to the Brouillon boundary. I have the completely flat band. So this flat band actually gives rise to diverging density of states, which is actually called the Fermi instability. So if I include the electronic correlation, at least in terms of the mean field Hubbard interaction, immediately I will see that there will be splitting between the top of the valence band and bottom of the conduction band, and this Fermi instability will be eliminated. So now I'll be having a gap created here. Okay, once you consider the mean field Hubbard Hamiltonian. Using the mean field Hubbard Hamiltonian, so this particular result has been verified with the experiment also, that if you have this kind of long zigzag edges, one have from the scanning Kalinin spectroscopy, one have seen that there is a gap at the band structure, at the Fermi energy, and there is a gap of the density of states also. Okay, so in that particular case, I have a gap which is actually verified by the experiment. So I know that mean field correlation is actually important in case of graphene. My question is, what is the implication of that? Implication is actually this kind of spin structure. The moment you have these edges, one of the edges will be all have downspin, other edge will be having upspin. That is the ground state solution of the mean field Hubbard Hamiltonian. Okay, so once I have that, that means I have ferromagnetic correlation along one edge, but antiferromagnetic correlation between the two opposite edges. So as a whole, I have the antiferromagnetic. I do not have any net magnetization, but on a single edge, I have actually magnetization. I want to make use of this particular aspect to design the valley polarization. How do I do that? I consider, this is the graphene case. I consider a super graphene system. What do I mean by super graphene? I want you to look into this particular structures, and I want to notice one thing. I have this A and the B sublattice points in the honeycomb lattice in the left-hand side. Now to correlate in the other side, I have again drawn that honeycomb lattice. Do you see that this black dot and the white dot, they are replaced by a triangle kind of unit consisting of 3 benzene rings, 3 hexagonal rings, 1 hexagonal ring pointing upward direction, 1 hexagonal ring, 1 triangular hexagonal rings, they are pointing downward direction. Okay, so if I compare this proper graphene structure and the super graphene structure, the difference between these two is actually, in one case, these atoms are actually carbon atoms are replaced by a triangulin unit. But the symmetry of the system remains same. It is still the honeycomb lattice. Okay, symmetry. So what is the impact of this one? Now, if you look into the edges, do you see that these edges are actually zigzag? Right? What does it mean? If you have the zigzag edge, I would expect the spin localization. Just now I have shown you. The moment I create the zigzag edges, I will actually have the spin localization. Okay. So this particular system does not, it has an inversion symmetry. Okay. So it should not show you the valley polarization. Okay. Now what I'm going to do actually, I'm going to consider one of these triangular units that I call a triangulate. Okay. And simple tight binding calculation will give me this kind of spin structure. This green and yellow, they are actually representing the upspin and the downspins. Okay, there is a spin polarized tight binding calculations is done here. So Na and Nb actually is shown here, and you can see that you have one of the spins higher than the other spins. You can see the green circles are larger than the yellow circles. So I put here S not equal to 0, that means total spin is not equal to 0. you have some net magnetization here. Okay. Question is that I am using a small triangular units, right? Is it experimentally possible? Answer is yes, experimentally possible, because people have actually synthesized exactly the same triangular unit very recently, okay, on copper surface and the xenon, okay, condition people have actually observed. Yeah. Here? This one? No. This is just these are right. These are actually I passivated by hydrogen. Otherwise, I want to have a two-dimensional system, right? If I want to have a two-dimensional system, these are all sp2 hybridized. So sp2 hybridized carbon should have 3 bonds. So if I do not passivate those dangling electrons, they are going to create some problems. Okay, they will come very near to the Fermi energy. So I do not want them near the Fermi energy. So to make them away from the Fermi energy, you just put those hydrogens. So those extra electrons will be absorbed by this hydrogens itself. They will be used for the bonding formation with the hydrogen. Okay, so those are the hydrogens. This is theoretical model. Let me see. Okay, so this is theoretical model, purely theoretical model. Now I am showing you a triangular unit. I showed you this kind of electronic localization. I show you the AFM picture of that. Do you all see that these bright spots here? These bright spots here? Those are related to these larger lobes. So electron densities are indeed larger, okay, at those corners. I want to join such two triangular units, just like what is happening here, right? One triangular, other triangular, coming in the opposite direction and joining, right? So I joined that two. One of them is giving green kind of spin more. Lower one is giving yellow kind of spin more. Total spin is now equal to 0. That is called a Clark's goblet. And again, that is experimentally synthesized structure. You can see on the gold surface, these are the 1, these Clark's goblet units. And you have indeed larger electron density along the edge, whatever is actually theoretically proposed. So these are all theoretically proposed, then experimentally achieved. Now I ask you one question, that is the question that you asked me, that, okay, this is theoretically predicted model. These are the single quantum dot units. To achieve this one, I need to keep on attaching these things and generate a two-dimensional mat out of that. Okay, is it possible or not? Answer is yes. People have done that. So this is what you are asking for, right? So people have done that. This is the real STM picture of that. And this is a very, very nice regular two-dimensional pattern people have actually generated. This is a 2D network of the triangle. The exciting part is that the angle resolution photoemission spectroscopy of this one shows the existence of the Dirac electrons in the supergraphene also. So the Dirac electron is not just the property of the graphene, it is property of the hexagonal lattice. So this system also shows the existence of the Dirac electrons. So I still have the linear dispersion at the Dirac points existing in this supergraphene structure also. Okay, now what I told you, this is the supergraphene structure I told. Here, exactly the same structure I have plotted, but now I have taken into account the existence of the spins also. I showed you if the upper directed triangle is hosting a downspin, the lower pointed triangle will host the upspin, right? I told two opposite direction of the triangular units will host upspin and the downspin, right? So in the unit cell, I have the two triangulins coming from the opposite direction. They are hosting two different spins, upspin and the downspin. Okay? Do I have the inversion symmetry anymore in that unit cell? I do not have the inversion symmetry because the moment I have the spins, upper triangle is having upspin, lower triangle is having the downspin. I put the inversion center here. I do not have any special inversion symmetry associated to this particular system. So the moment I incorporate the spin, actually, inversion symmetry gets broken and I have the strong localization of the spins, which is acting as a Mott insulator. So this system is actually acting as a Mott insulator. How do I know that it's acting as a Mott insulator? So I have actually plotted here the band structure obtained for the non-magnetic. That means this structure without the consideration of the spins. Red lines with this one after consideration of the spins within the mean field theory. Okay, what do I see? The antiferromagnetic structure is more stable as compared to non-magnetic. So it actually prefers to have the spin structure. Gap in the non-magnetic is 0. The black dotted lines at the Fermi energy, gap is 0, but it is still linear dispersion. Once you have the spins associated to this one, these two bands, which I called a conduction Dirac band and valence Dirac band, they separate out from each other, they opens up one gap. What is the advantage of that? It is a essentially gapless system. Now, because of the spin, I have a gap. That means I have valley. Okay, so I needed a valley, right, in the graphene system. Now I do have the valley here. Okay, and now if I actually try to compare the Minfield-Hubbard model with the density functional theory, I see that the T equal to 0.1 and U equal to 0.63 EV, it actually gives you very good agreement with the density functional theory and the Minfield-Hubbard Hamiltonian. What does that mean? In Minfield-Hubbard Hamiltonian, the correlation strength goes as U by T. So here U by T is actually 6 here. That means it's a highly correlated system. U by T 6 means it is in the Mott insulating phase. So that is why I am calling it as a Mott insulator. So in this particular system, now if I show you the Berry curvature, actually, Berry curvature for two different spins at the K and K prime valley shows such kind of different Berry curvature for the valence Dirac band and the conduction Dirac band. You can see the opposite. In place of red, there is blue. In place of red, there is blue. So at the two different valleys, you indeed have that one. But I want you to notice one thing. What is the value of this Berry curvature here? It is 2 to minus 2. Do you remember what is the transition dichalcogenate I showed? Plus 80 to minus 80. That means one order of magnitude higher. So here it is extremely small, right? But the question is that with this extremely small Berry curvature, will it indeed show the valley polarization in experimental scenario or not? That's a questionable thing. Okay, I do not have a robust valley polarization here, but although this is actually reported in theory that this will show the valley polarization. Now I will show you something. If this is the valley polarization actually, then I had this HBN structure at the beginning I told, that also breaks the special inversion symmetry, and I would expect the valley polarization in this one also because I have broken inversion symmetry. So Ranjan, here is the band structure. So I do have almost close to 5 electron volt gap here. Okay, and I have a valley at the K and also at the K prime valley also, same band structure. But there is one little problem here. These valleys are not really well defined valleys, because if you see the M to K, the conduction band is almost flat. Okay, so the moment I have the phonon participation, there can be excitations going from valence band, top of the valence band, to the conduction band in a particular range within the M to K if I have the phonon participation. That is one of the drawbacks of this HBN. But whatever it is, I actually indeed can expect the valley polarization. Okay, because it satisfies. That's how the bipartiteness is actually kept. Yeah, so you are right that up-down symmetry is still there in the sense that always the nearest neighbors are actually having up and down. Okay, but number of up and number of downs are not same in a single triangle. You are right. That's why I told when you have the single triangle in, you do not have that bipartite symmetry kept. You need to have, because a bipartite symmetry will always give you S equals to 0. That's a Leib's theorem for the bipartite lattice, right? When you have the same number of A and B sublattice points, you will be having net magnetic moment to be 0. Here you do not have the same number of A and B sublattice points. That's actually creating this one. That's a deviation from the Leib's theorem. Okay, but there you have the Na is equal to Nb, but the total number of Nas in this total and total number of Nb in the total class goblet you have to consider, not in a single triangle. So in that way, the bipartiteness is actually kept there. That no, I understood. Right. But you know the energy scale, actually I understand what you are asking, but the energy scale I think non-distinguishable, at least experimentally. It might happen theoretically, I agree. Yeah. In principle, one can right. Exactly. But still the Dirac point is coming very near to the Fermi energy actually. So length means the energy scale will be very means indistinguishable in my opinion. Okay. So am I audible online? Okay. Yeah, sure. Including the time lost here. Okay. Okay. So I would expect the valley polarization in hexagonal boron nitride. Okay. I told you that the moment I have very small dimension like these two-dimensional systems, I have the higher Coulomb screening, and because of that, I will be having considerably large electron hole scattering or the exchange between the two values. The moment I have scattering between two values, actually, optical selection will actually break down. Okay, so I cannot actually expect any kind of valley polarization here. That is precisely actually might be happening in case of HBN. Okay, now what we have to do? We have to then first try to figure out how much considerable this electron hole exchange or the scattering processes are there in case of HBN. Okay, now this electron hole scattering process, whatever I have shown here, actually, there is a 2 electron Feynman diagram that I have shown, right? Okay, so that means one has to consider at least a 2 electron part of the Hamiltonian. Single electron Hamiltonian will not actually work here. Okay, so that is why the many body interaction, at least the 2 body interaction, is actually very necessary, and we have to incorporate that. So for that, what we have done, we have actually taken into account the GW and GW-BSE. What is GW? G stands for the Green's function, W stands for the screen Coulomb interaction or the self energy in the Dyson's equation. Okay, now this GW, only the first order up to Dyson's equation has been considered here. Okay, one can actually go. So what we have done, we had gone just second order Dyson series also. We have checked the consistency of that one, but we have seen that not much changes there. So the second order Dyson's equation does not have, the second order term does not have much impact. Okay, so we had restricted ourselves up to the first order Dyson series. So the GW can be considered as G0W0. That means the first order term of the Dyson series. And G0W0 plus BSC, that is a Bethe-Salpeter equation. I'll just briefly tell about that. So here, with this coupled electron hole excitation, we consider any of the particular Kate states in terms of this equation, where I have used this A dagger, B dagger, with the subscripts V and the C stands for the valence band and the conduction band. So both are the dagger operators. So that means electrons and holes created. So this is a pair of electron holes. That is the exciton. Okay. So that is the exciton creation operator. And this A, that is actually electron hole coupling coefficients, and we name it as an envelope function. Okay. This A, nu, C, that S, envelope function. Okay. So whenever this particular operator operates on a null state, the vacuum state, it will create this excitonic state S here. Okay. Now, using that one can actually incorporate that in the Dyson series. One can do the Z0W0 calculation, and then through the Bethe-Salpeter equation, one can incorporate in the second term, represent the 2-electron interaction term or the Feynman diagram that I had shown in the last slide. Okay, so these are 2-electron interaction term, and this KEH, that is a 2-electron hole, this interaction. Okay, so that actually gives you the correlation between the hybridization or the scattering between the two valleys. Okay, the second term will actually incorporate. Once I solve this particular equation, we'll get this. This is the eigenvalue equation. So we will get this as this envelope function as the eigenstate of this particular equation. So the electron hole strength, actually a coupling strength, will come as a eigenfunction of that one. And using that, actually we can calculate the optical absorption considering the imaginary part of the dielectric function using this particular equation, where P is the polarization vector. Okay, so once you excite the electrons with the omega, then with this Dirac delta will give you the excitation at only the imaginary part of the dielectric function we are considering for the absorption spectra here. So this is the methodology we are actually adopting. So here is the band structure of hexagonal boronite, right? And you can see the dotted line is actually for the PB, that means just the single particle electron consideration, and the red lines are the Z0W0. After the self-energy correction of the Dyson series up to the first order, you can see there are actually differences. The gap has actually increased here, right? Once you consider the self-energy correction, that is the red lines having the larger gap there. With that, one have now the absorbance in terms of the photon energy is actually plotted here. And one can see once you have this electron hole exchange, you can have the exciton energy, exciton binding actually happening here, exciton formation in this particular A, B, C peak, which are all lower than the conduction band edge, that is a blue line. That means excitons are very stable as compared to the gap. So the excitonic states are actually happening in the mid gap between the valence and the conduction bands. Okay, so the stable excitations is getting formed. And here I have plotted the envelope function. Okay, the A that I had showed in the previous slide. Envelope function, if you see for these three different peaks, A, B, and the C, you can immediately see that K and the K prime, in between that, there is non-zero scattering. Zero means it's completely black, but none of the plots are having completely black region in between the K and the K prime valley. That means there is continuous electron scattering or the exciton scattering between the K and K prime values. Because of the scattering process, the valley degrees of freedom is getting completely suppressed. So no optical rule is actually getting followed. It's completely breakdown of the optical selection rule is actually happening here. The moment that happens here, actually, it doesn't supposed to show also the valley polarization, and that is why experimentally nobody has found valley polarization in the HBN. So what is the bottom line? That whatever we have discussed so far, that for the system, one should have actually broken special inversion symmetry. One should have gap at the valleys and all these things to achieve the valley polarization. But on top of everything, if all these criteria are also satisfied, if the exciton scattering is considerably large, one can never have any valley polarization. So one should have very, very minimal exciton scattering. So whatever the result I had shown, whatever the result that I have shown, okay, that super graphene structure where the valley polarization, the Berry curvature value is just +2 to -2, it is varying. So it is now questionable. Can you check whether the intervalley scattering is there or not to suppress this very, very small Berry curvature or the very, very small pseudomagnetic field? Okay, so it can be completely destroyed once you have the electron hole scattering. Yes. No, anything. Oh, doesn't matter. It all depends on what is the scattering or means exciton lifetime and all these things. Okay, recombination rate basically you are talking about. So excitons can be formed in a 3D system also, but if the lifetime is very, very short, then they will immediately recombine with each other. Those are not detectable, but the theory should be actually valid there. Understood? Okay. Now I showed you the graphene, the super graphene, and hexagonal boron nitride also, right? So it seems graphene doesn't show, hexagonal boron nitride doesn't show valley polarization for different reasons. Super graphene actually shows value polarization, but very, very small vary curvature, +2 to -2. What I have done actually here, so we have taken the super graphene structure. Okay, I have these hexagonal vacuum regions. This kind of system, as Koteshwara actually mentioned, experimentally achieved, but at low temperature. The moment you have elevated temperature, these edges undergoes reconstruction. You do not have the zigzag well-defined edges anymore. Spins get suppressed actually. The spins get suppressed spins. Again, you do not have any broken special inversion symmetry and you lose your value polarization there. Okay. So I need to suppress the reconstruction even at elevated temperature also, so that experimentally it is actually measurable. What I can do, I can fill up these particular gaps. I call it as graphene kagome because it actually looks like a kagome-like structure, right? Maybe now it is in the region of Ranjan and Sambuddha, kagome lattice structure. So graphene kagome, what we did actually, you take this graphene, fill up this hexagonal gap with hexagonal boron nitride. Why is it so? Because the lattice mismatch between graphene and hexagonal boron nitride is just 3%. Okay, so very easily actually one can seamlessly they can actually attach. Okay, I'll show the experimental proof also of that. Okay, similar kind of structure. So I'll fill up with boron nitride. How it will actually help me? I do not have any edge. So at very elevated temperature also, this system will be sustainable. Okay, so experimentally achievable structure. And experimentally achieved that I will actually show you also. Okay, that is what I have done here. So I call it as a graphene kagome filled with hexagonal boron nitride. Counterpart of this one, I can consider a hexagonal boron nitride kagome lattice, right? Same lattice, instead of super graphene, I can consider super hexagonal boron nitride with boron nitride alternative units here. And then I can fill up this gap by hexagonal graphene patches. Similar kind of structure, right? Only both of them are counterpart of each other. So this is this particular structure where I have HBN kagome filled with the hexagonal graphene. Now, if you look into both of these structures, actually, the special inversion symmetry is actually broken here. Look at these two unit cells or the super cells. Special inversion symmetry is broken in both the cases. One would expect some kind of value polarization. I have valleys here. I have broken special inversion symmetry also here. So one would expect. So here I have plotted the super graphene. I have shown you this picture also before. Now I show the super graphene with hexagonal boron nitride filled within the hexagonal patches. Okay, this shows this kind of band structure where the direct band gap is 1.17 eV within the single particle picture, and I have valleys formation at the K valleys also, right? You can see it's rounded valleys at the K. Okay, carrier mobility theoretically calculated goes as this one, which is comparable to graphene also. So this particular system, the carrier mobility is actually comparable with graphene, very high carrier mobility, this particular system. Okay, I see the Berry curvature. I indeed see the Berry curvature, positive and negative, in two valleys, K and the K prime valleys. I want you to notice this value. In the atomic unit, it goes to 60 to -60. What I have done, instead of super graphene, where the Berry curvature values are just +2 to -2, I filled up the super graphene patches, the gaps, with the hexagonal boron nitride. I can enhance the Berry curvature by 30 times, 1 order of magnitude higher. Okay, so very high Berry curvature, which is comparable with the transition metal dichalcogenide system. It seems promising for the valuetronics, right? All the criteria are actually satisfied. But now we have to actually remember one caution: interval scattering, right? If I have the very large interval scattering, everything will be getting suppressed. Okay, so this is a G0 W0. This actually excited. The gap is actually increased. I have the singlet exciton also formed, which is a binding energy here. Okay, all nice things. Okay, very stable exciton is actually getting formed. Now I plot the envelope function. The moment I plot the envelope function, immediately you see very large interval scattering between the K and the K prime values. Very large. It doesn't disappear at the middle. Okay, this is the color code varying from 0 to 1. Okay, so in between two values, I have very large interval scattering. So once I have the very large interval scattering, value polarization is unlikely to happen in experiments. Now think about that. This particular material has shown Berry curvature of +60 to -60. Still, it doesn't show. It should not show the value polarization in experiment, right? So whatever I had actually shown +2 to -2 is also not supposed to show any value polarization. Okay. Now I take the counterpart. I take the Kagome structure of the hexagonal boron nitride, and it is highly insulating. And you see the top of the valence band, bottom of the conduction band, all are flat. I do not have any valley there. So no question of having any valley polarization in simple Kagome structure of the hexagonal boron nitride. Once I fill up those patches with graphene, immediately I see that there are formation of valleys and the K and K prime. That plot is actually this circles I have actually given. The circle actually stands for the gray contribution of carbon, and the blue circles total contribution from the boron and nitrogen. So you can see that both the bands, the top of the valence band, bottom of the conduction band, they are actually made of carbon, boron, nitrogen, everything, but the maximum contribution is coming from carbon because the radius of the circle is proportional to the contribution of that particular element. Okay, so I have that. So I have the direct band gap 1.81. Charge carrier mobility again is very, very high, almost comparable with the graphene. Okay, I see the Berry curvature. I indeed see the opposite Berry curvature, +36 to -36. Again, it seems to be promising for the valley polarization. Then I calculate the optical excitation. I see very stable binding energy of 0.8 eV, excitant binding energy. Before I go to the valley polarization, something more interesting actually, or something very interesting we have seen in this particular case. Okay, what we have done, these are the absorption means only the optically allowed peaks are actually shown here. But we have calculated the density of states of both the triplet and the singlet. We know that the singlet states are actually dark states. They will not come in the optical absorption. Okay, so I've shown both the triplet state. The top panel is a triplet, the up electron up hole, bottom panel is singlet, up electron down hole, singlet states. Okay, singlet state, you see this is the peak A corresponding to this one. You can see I masked actually some of the other singlet state also. Those are the dark singlet state, optically not allowed. So no excitation will happen. So optical excitation will happen only from the peak A. Okay. Now you see the gap between the first triplet excitation and first bright singlet excitation is almost 0.46 eV. That means the triplet state is 4.46 eV stable as compared to the singlet state. So this particular system shows much more triplet excitation as compared to the singlet excitation. What is the advantage of that? The quantum efficiency will be very, very high for the light harvesting. Okay, because one needs a triplet excitant for the larger light harvesting. Okay, now if I come to the triplet state and the envelope function, the triplet state shows strong intervally coupling. I cannot have valley polarization in terms of the triplet excitations. Okay, what we have done, we wanted to see from where these contributions are actually coming, and we see that contributions, this is a triplet, and I have indexed this one with valence band 1, valence band 2, valence band 3, conduction band 1, conduction band 2, conduction band 3. Okay, now you can see that for the triplet, for the V1 to C1, that means valence band maxima to conduction band minima, 77% transitions are actually happening. But there are non-zero transition between the valence band 2 to conduction band 2 also. So other bands are also participating. So here I have plotted the envelope function for only transition from valence band maxima to conduction band minima, and we see that if the excitations are happening only between the V1 and C1, one can actually see the valley polarization. But the contribution from the other bands, since they are also flat in nature, you have the excitations happening those places also. Okay, because of that, you have suppressed valley polarization and the intervalley scattering all over the Brillouin zone. Okay, this is for the triplet excitant. What about the singlet excitant? If I see the singlet excitant here, the V1 to C1 is 97.9% actually, and rest of the things are very, very small. So mainly for the singlet excitants, only from the top of the valence band to the bottom of the conduction band, the excitations are actually happening. So here I plot the envelope function, and immediately you can see that there is negligible scattering between the K and the K prime values. So now we can say that maybe this system is actually capable of showing the valley polarization. So what we did, we further applied the two different circular polarized lights, and in presence of two circular polarized light, sigma plus and sigma minus, we calculated the oscillator strength. Okay, for the optical excitation. And for the sigma plus, which is a left-handed circular polarized light, you see the excitations are happening at K values. In presence of sigma prime, excitations are happening only at K prime values. So in presence of two different circular polarized light, they selectively couple with the K value and the K prime value. So this particular system can show as a very, very efficient value polarizer. Okay. If I do not have time, I have a second part, but I will not show. I'll stop here. Okay, fine. I'll stop here. Okay. So just give me 2 minutes. I'll wrap it up. So now that is what I wanted to tell, that although this system showed, okay, that non-zero Berry curvature, maybe this system is not capable of showing the actual value polarization because it is very, very suppressed this one. So one needs to check whether this is actually possible or not. Okay. Hello. seen the value polarization for this kind of systems also, this two-dimensional system, two-dimensional graphene system. Okay. So in conclusion, what we have seen that broken inversion symmetry in lateral heterostructure of graphene and HBN, that is a borocarbonitride system that we have studied, that can show the non-zero Berry curvature. But strong electron hole exchange can actually suppress this value polarization even for the very high Berry curvature also. And whether you see the value polarization or not, that actually crucially regulated by the extent of the intervalley scattering. Okay. So these are the references. There are 2 papers we recently submitted, and in journal and also archive we have uploaded. So anybody interested, maybe you can actually go through these 2 papers. Detailed calculations actually is actually given there. Okay. So I thought that maybe I'll just briefly mention about whatever we are doing in our group. So basically we work on the low dimensional system. You use the external perturbations. One thing I have shown here, external light or the electromagnetic radiation. Similarly, we apply the different kind of perturbations and we see the possible applications for the low dimensional system. Basically, transport, we observe, we consider the electronics in molecular and the small diode applications, two-dimensional magnetism, and then the hydrogen oxygen evolution reaction in terms of the green energy applications. Then topological superconductor in terms of layered intercalated superconductors, and the Dirac on the wild semimetals and the topological insulators, and quantum phase transitions. And we basically use different analytical and computational techniques like tight binding, mean field, density functional theorem, many-body theory, and we develop mostly our code in our group itself. So I want to acknowledge our present group members, and all of them are actually working in different fields, and whatever work I have shown today, this is done by Shoren. Okay, so he will be defending his thesis maybe this month. So he is the first PhD student from our group, and whatever work I have shown today is a part of his thesis. And I would like to thank DST and IISER Tirupati for the funding, and thank you. Yes. So
from online.
Is there any question from online? You can please unmute and ask if you have any question, the online participants. Okay, maybe not. Yes, right. It is 1/r only. No, it is 1/r only. It is 1/r only. It's a Coulomb scattering itself. But it's happening for these particular states. These new C states are actually these states that you have considered. So now the basis is in terms of the exciton basis. Okay, the basis itself is an exciton. So you are considering the exciton scattering here. Okay, but 1/r only. Yeah. No, these are the two particle states. These are the excitonic states. That's what I had written here. Yeah. So the creation will be happening in terms of the two creation operators. Annihilation will be happening in terms of the two annihilation operators. Okay. So now you are not just creating or annihilating a single electron. You are annihilating the exciton itself, which is a bound pair. Excitonic states. No. These are two particle bases. Exactly. Yeah, they are one particle. Yes. Yeah. So this form is 1 over r only. Operator form is 1 over r. Yes, orbitals we have not DFT actually. So on top of DFT, we have performed this G0 W0 calculation. With those orbitals, actually constructed this one. They are kind of Gaussians, yes. You can say those are the Gaussians actually. Yes, 1 year orbitals basically. Yeah, localized orbitals, not the plane waves. Yes. Yeah. Does it answer your question? Yeah. Any further question? Sorry? Yes, that is another reason. You are absolutely right. Because of this flatness. Okay. So the valley itself is not very well-defined valley is there. That is another reason that why you are having this one. If you remember, the similar kind of thing actually happened for the triplet exciton state that I have shown also. Okay, because of the flatness between the gamma and M, there are excitations between those places also. Okay, so when you have flatness of this band edges, that actually acts negatively towards the valley polarization. Okay, yeah. Because the valleys itself are not very well-defined valleys. Yeah. Scattering process in terms of the right. You indeed have the impurities when you actually consider. See, hexagonal boron nitride is one particular material that you can actually experimentally get very clean system, very clean. That is why hexagonal boron nitride is actually being used for device fabrication for any other 2D materials. Those are used as a substrate. Okay, those are used as a substrate means they do not have much interference to the actual property of the actual channel that you are actually using. Okay, so hexagonal boron nitride is very clean. But if you have the different scattering centers in terms of the impurities, they will actually add up to these scatterings also, intervally scatterings. So that is something you do not want to have in your system. But what Sambuddha was asking actually about the conduction property of this one. If you have the Dirac electrons, like the supergraphene system and all, okay, then you have the Klein tunneling property there coming from this hexagonal lattice property. Klein tunneling means you do not have any barrier there, barrierless tunneling. Okay, so then really you don't care whether you have impurities or not, because impurities doesn't scatter those Dirac states. Okay, but if you are not dealing with the Dirac electrons, like transition metal dichalcogenides or all, those are not the Dirac material, Dirac electrons. There, if you have the impurity, they will actually add up to this scattering also. Okay, right, impurities will add to the scattering. I understand. Interesting idea, but I do not have. You mean to block the scattering process actually by some external means? Interesting idea, but I am not aware of. Right. I totally understand. I understand. Yeah. Right. I think what you are proposing, I don't see any reason why it should not happen. Definitely it is possible. I am not aware of. That's what, but it's very interesting idea. I'm not aware of, but what you are saying actually, designing the things in that way, I think it is possible. Surely it is possible. Yeah. I have to see. Nice idea. Maybe some study can be there. I'm not very sure. You can see the most of the papers actually came after 2020. So very, very nascent field at this moment. Yeah. Thank you.